Hi, my name is Darren Doherty. In this project, I'm going to be going over a tool I developed in R for validating sample groups. We will be looking at it in the context of medical trials, but the great thing here is that you can apply this to any workflow where you are comparing things. It could be insurance or quality control in manufacturing, for example, but here we are in the world of healthcare. So let's meet Doc and go over the use case of this tool. This is Doc, and Doc is a doctor. Specifically, Doc is a researcher who wants to conduct a medical trial. And to do that, Doc needs a sample group. Doc works at a university that maintains a database of candidates for medical trials. The university has provided a group of 1,000 potential candidates for Doc's trial. Doc splits the group into two equal subgroups so that he can conduct his experiment. It doesn't really matter what kind of trial Doc is performing, but for an example, we can say that this trial will be focused around evaluating a new drug. Doc assigns the first group of 500 to be the control group. In this group, they will be given no medicine or perhaps a placebo. Doc assigns the second group of 500 to be the experimental group. They will have the medication administered and the effects studied compared to the control group. Great. Let's begin our trial now. But wait, says Doc. We need to make sure our two groups are similar enough for an effective study. And why is that? Because different factors could impact the effects of the drug we are researching. And we want to make sure any effects we observe are from the drug itself and not some kind of outside miscellaneous factor. Doc thinks of several things that could throw off the results of our trial, like if one group on average is older than the other group, or what if one group exercises more frequently, and could other medical conditions affect the outcome? Doc wants to compare the two groups to make sure that factors like these are similar enough to not affect the study, or so that any differences are measured and can be accounted for. Like many scientists and researchers, Doc uses R to analyze his data. Let's explore what Doc will be doing in R. We will be using a package in R called Quarto, which generates reports with embedded R code inside of them. This allows a report viewer to run relatively complex R operations with just a click of a button and no programming experience required. Our report will ingest a formatted CSV with the columns listed here. We have ID, which is just a serialized numeric identifier. Study group can be one or two, one being our control group, two being our experimental group. We want to track the candidate's age and gender, which in its clinical sense just refers to their binomial birth gender. We have a few medical conditions the candidate could have a diagnosis of, but we also want to track their physical activity, net income, and daily sugar consumption. As with any application that ingests data, it's important that the CSV is formatted correctly with consistent column names and data types. Here is a larger view with example formatting for our CSV using the columns that I just described. Awesome. Let's go over to the report itself and take a look. And here is our quarter report. There's a lot going on under the hood with the embedded R code, but the user interface is actually pretty simple. Let me walk you through it. At the top, we just have a brief description of the purpose of the report, followed by the required R libraries to run it. The libraries actually load automatically when the report is rendered, but there are instructions to install in case they are not already on the user's machine. Below is the analysis section, which is an app created with the R package called Shiny. This is where all of our statistical magic will be happening. And at the end is documentation describing the formatting that an ingested CSV needs to have. And that is what I just covered on the last slide. Let's use our Shiny app and do some analysis. This is very simple for the user. All we need to do is load the CSV data we want to analyze and click some buttons. I will start with my first dataset and go through the app's functionality. Then I'll show some of these other datasets with unique scenarios in them. We will go ahead and load study sample 1, make sure that we get the upload complete message. Perfect. With our data loaded, we are free to use these buttons to compare the control and experimental groups. The first thing we will pretty much always want to do is generate our summary table. So let's go ahead and click that button. Our table shows rows for all the attributes I previously described. In the columns, we have statistics for the entire dataset of 1,000 candidates, the statistics of Group 1, control, and Group 2, experimental, respectively, the absolute difference between Group 1 and 2 and their associated measurements, and by that I mean age is in years, income is in USD, like that. And the last column, though, is probably the most important if we had to pick just one. It takes this group difference column and divides by the dataset mean. So it pretty much shows how much the groups differ from each other as a percent. As a general rule, Doc wants his two groups to have no more than 5% difference, and in our difference percent column, that would be a value of 0.05. We can see that most of these attributes do meet that goal of 5% or under, but there are two that exceed it. Namely, the difference in diabetes positive candidates is 12%, and the difference in melanoma positive candidates is 7%. That doesn't immediately mean that Doc will reject this entire sample group, though. Doc can use his medical knowledge to determine if these factors are significant enough to the specific drug trial he is wanting to run. In order to do that, we can also inspect all of these attributes more closely with a visual comparison. For example, let's take a look at a category that does meet our 5% goal. Sugar consumption only has a 2% difference here. We can scroll down and generate some box plots of sugar consumption to visually examine the differences. We have our group 1 on the left and group 2 on the right, and because they only had a difference of 2%, the box plots are pretty similar as expected. Let's take a look at diabetes positive candidates, which had a difference of 12%. We click to generate our pie charts, and again, we have group 1 on the left, group 2 on the right, and we can easily see the difference here. Blue shows negative diagnosis and red positive diagnosis. It's readily apparent that there are more positive diagnoses of diabetes in sample group 2. So if Doc deems that significant enough to his study, he may choose either to reject the entire group of candidates or just make a note of the differences. When he includes that in documentation for his reports, it's already measured and visualized here for him. We saw sugar consumption and diabetes rates. Let's take a quick look at visuals for the other measures. Our ages are compared with a histogram. This one will combine and overlay the two groups and shows their distribution over various age brackets. Blue is group 1, red is group 2, and the spaces they overlap are this kind of purple strawberry jam type color. In theory, we are checking to see how similar the groups are. Therefore, the more strawberry jam, the better. And we do see a lot of strawberry jam here. In the places where one group does have more people in that age bracket, the differences are not too large and they are pretty evenly spread out. And that's kind of what we would expect to see because in our summary, the difference was only 1%. I'll skip down to our income comparison because it follows the same format. Again, we see a histogram with both groups overlaying each other, and we see lots of strawberry jam. Income does have a slightly bigger difference of 2%. We see the larger areas where there's only one group represented, but since they are fairly evenly spread, the law of averages makes it pretty even when looking at the entire sample group of 1,000. If we do want to get into the weeds a little more, this visual comparison does provide context and lets us make note of a few things, like that group 2 does have more high earners. At the time of this video, average household income in the US is roughly 80,000 a year. If we look at that area on the chart, which is everything right of about right here, there definitely are more candidates from group 2 with above average income. This could lead us down a rabbit hole of access to medicine versus disposable income and cost of living, but I will steer us back on course to the next visual. Gender, diabetes, arthritis, and melanoma, these are all percentages that we're comparing. So a great visual for that would be pie charts. We already saw the diabetes, which has a difference of 12%. That's very readily apparent here. But we can take a look at gender as well. almost equal. We can see our arthritis, pretty close, and melanoma. There's a difference of 7% here, and you can see that if you look closely. Now, physical activity was pretty interesting. Our responses to that were actually text information. Let's peek down here at the formatting documentation. Candidates self-reported their physical activity level as either none, light, moderate, or heavy. I took these responses and gave them numerical values, 0 for none, 1 for light, 2 for moderate, 3 for heavy. And then graphically, I represented these as side-by-side column charts. We can see they are mostly equal, with a few more moderate in group 1, a few more heavy in group 2. But the big thing here is the shape of the graphs helps us to establish deeper context. We saw in our summary that overall there was only a 3% difference, but the thing is that 3% could come from a wide variety of ways. You could have in one group a lot of light and moderate, and then in the other group you could have none and heavy taking up the majority. But because we can see these side by side, Doc can tell that not only overall do the two groups match closely as a percentage, but the components that make up that percentage are pretty evenly spread. The last visual is our sugar consumption, and we're using box plots to look at that. We saw this already briefly, but I'll go ahead and give a quick overview of it. Box plots are pretty handy when you're looking at a wide range of numerical values, and the random data I generated allows a candidate sugar consumption to be anywhere from 0 to 100 grams per day. I didn't weight these, so in this example, we have a pretty even distribution of the 0 to 100 range. Let's focus on the red group 1 plot just to understand the parts. The line in the middle is our median sugar consumption for group 1, which, as you can see, is just slightly over 50. The lines that extend up and down are called the whiskers, and they show the minimum and max values for the data set. Here we see the minimum is 0 and the maximum is 100. The lower edge of the box is the lower or 25th percentile, and that's the median of the entire lower half of the data. The upper edge of the box is the 75th percentile. In real life, you won't usually see data so evenly and perfectly distributed on a scale from 0 to 100 like this, but it really does help you understand the box plot when you see it here. The 25th percentile just happens to line up right around 25. The 75th percentile right around 75, and the median right around 50. Now that we've seen all the functionality of the report, we can run quick analysis on a few more data sets and maybe see some interesting scenarios pop up. We can load a new CSV while the report is running, and it will automatically update everything. So let me load study sample 2, which is formatted exactly like what we just saw. 1,000 candidates, 500 in each group. Our table automatically updates, and we can see this might be a better group for Doc. There's only one attribute which goes over our 5% limit, which is mean physical activity, but everything else falls in that range. If Doc had a choice between the two groups, he would probably want to choose this one. Let's look at study sample 3, which I did as a bit of a stress test for the report. Designed the report in just 1,000 candidates, and this one contains 10,000. Let's see how it performs. R is beautifully fast, and the table updated almost instantly. And we see a pretty basic statistical concept play out, law of large numbers. As we get a larger group to examine, there's less variance overall. Most of our difference percentages are 1 or less. Our greatest, which is 3, is for gender. Most of our visuals are going to be pretty identical too. So our biggest one was gender, 3%. Let's take a look at that. And the charts are almost the same. You can see a small difference if you look closely. Our histograms, for example, it's almost entirely strawberry jam. And then our sugar consumption box plots, almost identical to each other. Last, we have study sample 4, and we're going in the opposite direction. This one contains only 50 candidates, 25 in each group. Watch these percentage differences when I load it. These two groups have a lot of differences. Age, gender, and income all came out pretty close, but everything else not so much. This is why you always want the largest sample possible. Let's look at the melanoma pie chart with a 26% difference, and there's a big change there. Even our histograms like income, which only has a 2% difference, they are going to be much less useful. At least with our sugar box plots, this is much more realistic compared to what you'd see in real life. Our graph doesn't even go up to 100. Our maximum value is around 90. And the boxes show that the percentile ranges are much different too. Let's look at the real world applications for a report like this. The way I've structured it is probably not too useful for an actual medical trial, but I wanted to mainly show off the Quarto report's capabilities. In actuality, Doc would probably have a much more targeted set of metrics for his trial. So, say Doc was testing a drug to combat melanoma. He'd probably want to gather more targeted information about the candidates. The basic items like age and gender may be useful, but in my very non-medical expert opinion, I don't know if income or physical activity would be as relevant. Melanoma in general is skin cancer caused by exposure to the sun's ultraviolet radiation. Doc may instead want to see information about the candidate's time spent outdoors, so a construction worker and an office worker would differ a lot here. How consistently did candidates use sunblock over their lives? Candidates' race and, by extension, darkness of their skin would probably be a large factor, and location too. Sun's rays are strongest at the equator, and an area's climate could also impact those results. Last, let's think of other use cases for a Quarto report. The ability to empower anyone, regardless of their programming or statistics knowledge, to run analysis like this is where the Quarto report shines. Anytime you're making comparisons of groups, this is incredibly beneficial. Some examples I can think of are determining insurance rates, like based on location, and in auto insurance, a customer's driving records. Also manufacturing. Things like machining ball bearings require extreme precision. We could replace sample groups of candidates with batches coming off the assembly line, and when we see anomalies pop up, that warns us there may be an issue with the production machinery. Thank you for watching. I hope you understand a little more about R programming and the Quarto package. I can be reached by email with darren@darren.pro, or you can check out my new portfolio website, www.darren.pro. You can also reach out to me on LinkedIn, where my URL is just my first and last name. That being said, once again, thank you for watching.